There is a house standing in Namibia right now built from bricks that did not exist 8 months before the walls went up. Those bricks were grown by a fungus. The material that built them started in a dorm room. It grows in 5 days at room temperature from farm waste that would otherwise be burned. And almost no one is building with it. Why? To understand why, you need to understand what fungi actually are. Most people have it wrong. The mushroom is not the organism. The mushroom is the fruit. What you see above ground is temporary. It is a reproductive structure that pushes up, releases spores, and then dies. The real organism is underground. It is called mycelium, a dense web of tiny thread-like roots, thinner than a human hair, branching and fusing across acres of soil. It is, in many ways, the hidden infrastructure of every ecosystem on Earth. It breaks down dead organic matter. It binds the soil together. Every forest you have ever stood in exists partly because of it. Here is what matters and why this changes everything about how we think about building materials. When mycelium encounters organic material like corn stalks, straw and wood chips, it threads through every particle and fuses them together at thousands of contact points. It does this automatically. It does this because that is how it eats. Think of it like fiberglass, except instead of glass strands held together by synthetic glue, you have fungal threads holding organic waste together. The fungus is the glue. It grew there. It built the structure itself. The process takes 5 to 7 days. At the end, the material goes into a low heat oven, not to harden it, but to stop the fungus from growing further. The mycelium dies, the structure it built remains. What comes out should not exist. It weighs about 43 kilograms per cubic meter. Concrete weighs 2,400. In 2006, a 20-year-old engineering student named Eben Bayer was given one instruction by his professor. Find a problem worth solving and build something that solves it. Bayer had grown up on a farm in Vermont. He had watched fungi grow on wood chip piles, binding them into solid clumps. He knew mycelium would thread through almost any organic material. He wondered what would happen if he made that process deliberate. He seeded agricultural waste with fungal spores in his dorm room. He left it under his bed. A few days later, what came out was solid. His professor held it in his hands, turned it over and told him to start a company. Before Bayer graduated, he and his classmate Gavin McIntyre founded Ecovative Design in Green Island, New York, the first company in the world built around growing materials from fungus. The material's first commercial breakthrough came not in construction but in packaging. Dell, Puma, then IKEA in 2020 committed to replace polystyrene packaging worldwide. That was proof that this material could be produced at industrial scale, cheaply enough to replace something the entire global economy runs on. But packaging is not construction. The harder question was this: could mycelium composite become a structural building material? That question was still unanswered. In 2014, architect David Benjamin built a 40-foot tower in the courtyard of MoMA PS1, the Museum of Modern Art outdoor exhibition space in New York, using nothing but mycelium composite bricks. He called it Hi-Fi. The premise was simple. What would a building look like if its primary material was grown rather than manufactured? The tower stood for a full summer exhibition. It bore its own weight. It absorbed sound. Then, when the show ended, it was composted. 40 feet of structure grown from corn stalks and fungi returned to the soil when it came down. That demonstration did something important. It showed the world that this material could perform structurally at scale. Not theoretically, actually. 10 years later, in 2024, architect Christopher Mora took it further. Mora had spent years working on sustainable housing in Namibia, watching invasive acacia bush choke farmland across the country. He realised that the same plant destroying the land could feed the fungus, and the material left after harvest could be pressed into building blocks. The project was called Myco-Hab, more than 900 blocks, each one roughly 10 kilograms, strong enough to bear the weight of a building, comparable to the concrete blocks used for construction in the region. The walls were finished with mud plaster. the structure stands today. Growing those 900 blocks pulled 9 tons of carbon out of the atmosphere. That is not a pavilion. That is not an installation. That is a house. And in Newcastle, England, researchers developed something called mycocrete, a mycelium paste that can be injected into flexible fabric moulds, forming curved shapes that rigid moulds cannot produce. In 2023, they grew a self-supporting arched dome from it. No steel, no concrete, no heat. Cement production requires kilns running at 1,450 degrees Celsius. It accounts for 8% of global carbon dioxide emissions, more than aviation and more than shipping. Every year, the world produces 4 billion tons of cement. Every ton releases approximately 900 kilograms of carbon dioxide. The kilns run continuously on every continent because the construction industry cannot stop needing cement. Mycelium composite grows at room temperature from waste that would otherwise be burned, turning a carbon source into a carbon sink. Studies have found that it can be carbon negative. The carbon locked into the material outweighs the carbon produced in making it. For insulation, wall panels, acoustic tiles, and exterior cladding, the parts of a building that do not carry structural load but still represent enormous material volume, this is not a future material. It is a present one. So why isn't it everywhere? Here's where the honest version of this story gets complicated. Mycelium composite is not going to replace structural concrete, not soon. Possibly not ever for certain applications, and it's worth understanding why. The first problem is strength. Standard mycelium composite panels are not nearly strong enough for load-bearing walls in multi-story buildings. The gap between what this material can handle and what concrete handles is enormous, roughly the difference between cardboard and stone. But researchers are closing it, and faster than most people expect. The approach getting the most attention right now involves controlling the geometry of the material at a microscopic level. Instead of letting mycelium grow randomly through a substrate, researchers are building precise, three-dimensional scaffold structures printed in specific shapes that mimic the internal geometry of bone or coral, and growing mycelium inside them. The result is a composite where the fungal threads are aligned to carry load in exactly the directions that matter. A study published in 2023 achieved peak strengths approaching 16 megapascals using this method. That puts it in the same league as clay brick, not concrete, but genuinely structural for a wide range of building types. Single-story housing, low-rise commercial, the kind of construction that makes up the overwhelming majority of buildings on Earth. The second problem is moisture. This one is less dramatic but arguably more stubborn. Untreated mycelium composite absorbs water. When it does, it swells, softens, and loses the structural integrity the dry material has. In a climate-controlled interior, a wall cavity, an insulation panel, a ceiling tile, it performs well. Expose it to rain, humidity, or direct weather, and without protection, it degrades. Current approaches include natural wax coatings, bio-based resin treatments, and hybrid panels where a moisture-resistant outer shell encases a mycelium core. None of these are perfect, all of them add steps and cost. But researchers at several institutions, including teams in the Netherlands, the UK, and the US, are actively working on treatments that integrate into the growth process itself, so the material emerges from the mould already protected. That would change the economics considerably. The third problem is the one no researcher can solve alone. It's the building code. There are no official standards for structural mycelium composites anywhere in the world. Not in the United States, not in Europe, not anywhere. A designer who wants to use mycelium composite for walls that actually hold the building up today is writing in a language the building code does not speak. No standard means no insurance. No insurance means no contractor. No contractor means standard drywall and steel framing every single time. This matters more than it might seem. Building codes are not just bureaucratic obstacles, they are the accumulated record of every building that has ever failed. Every fire, every flood, every structural collapse, translated into minimum requirements. They exist because buildings kill people when they go wrong. The industry's conservatism around new materials is not irrational. It is the product of experience. But codes do change. They always have. Engineered timber, cross-laminated timber known as CLT, was a fringe material 20 years ago with no code recognition and no insurance pathway. Today it is specified in major buildings across the world, including high-rises. The path from laboratory curiosity to code-recognized material took roughly 2 decades of testing, lobbying, demonstration projects, and incremental standard setting. Mycelium composite is earlier on that path, but it is on it. The American Society for Testing and Materials, the body that sets the standards American building codes depend on, has working groups actively developing test protocols for bio-based building materials. The European equivalent is further along. The demonstrations are accumulating, the data is being generated, the code will follow. This is not a conspiracy. It is the normal friction of a new material entering an industry that moves at the speed of liability rather than innovation. Standards take decades. They always have. The question is whether the climate can wait that long. The science is not hypothetical, the production is not theoretical, the buildings are real. What's missing isn't the material. What's missing is the industry infrastructure around it, the standards, the insurance categories, the technical language. Architects and engineers use to order materials. That infrastructure takes time to build. But it does get built. It always does, for materials that work. The student grew the first version of this material under his dorm room bed. The tower at Momo was composted when it came down. A house in Namibia stands on blocks grown from invasive bush waste. The fungus doesn't care about supply chains. It has been binding organic matter into solid structures for longer than we have existed. It built the forests. It built the soil. Now it's building for us. The only question is how fast we let it.